Hi everyone, my name is Renjie Zhao, a PhD student of UC San Diego. Today I'm going to introduce our platform, MCube. It is an open-source millimeter-wave MIMO software radio for wireless communication and sensing applications. Millimeter-wave technologies represents a cornerstone for emerging wireless network infrastructure and for RF sensing systems in security, health, and automotive domains. Through a MIMO array of phase arrays with hundreds of antenna elements, millimeter wave can boost wireless bit rates to more than 100 Gbps as proposed in the millimeter wave Wi-Fi standard 802.11ay, and can potentially achieve near vision sensing resolution. To conduct research on millimeter wave massive MIMO, we believe a programmable experimental platform with the following critical capabilities is needed. First, it should be equipped with low-cost and large phase arrays, which represent the key features of millimeter wave radios. Second, it should support the millimeter wave MIMO architectures, which is to be used in 5G NR and 802.11ay. Third, fast beam swapping should be available, which allows real-time beam swapping to accommodate the high mobility networking or sensing scenarios. Fourth, it should allow reconfiguration of beam patterns, communication or sensing algorithms, and network stack. Unfortunately, to date, there is no widely affordable platform which satisfies all the capabilities, which is impeding the research in this field. Other researchers have also developed millimeter wave platforms based on self-built phase array, such as the OpenMILI project, or purpose-built front-end with discrete components, such as MMFlex or X60. This kind of design is typically expensive, and none of these existing platforms support millimeter wave MIMO configuration due to the limitations of this RF front-end. The NI millimeter wave testbed can be used to build up a 2 RF chain MIMO setup with third-party phase arrays, but the cost of over $100 per RF chain limits its adoption. Our MCube platform represents the first millimeter wave MIMO software radio to overcome these limitations and meet the aforementioned critical requirements. Our main idea is to convert a commodity multi-chain 802.11ad radio to an SDR, so that we can take advantage of the low cost of commercialized antenna array while keeping the flexibility of SDR. Our design will contain a flexible data path. It can use narrowband SDR or wideband ADC or DAC as BPU. Then we designed a real-time control path, which provides sub-microsecond latency to support fast beam swapping. We also investigate the phase array module to make the beam pattern reconfigurable. And finally, we designed the massive MIMO architecture with the commodity radio. We will first give some photos of the platform. First is the bridge boards, which separates STX module and RX module. This board serves as the bridge between the baseband data processor and the phase array module. Then is the 4RX MIMO setup. It shows the connection between baseband module, RX bridge board, control FPGA, and the phase arrays. The phase array modules are on the front panel, forming an 2x4 array of phase array. The host PC controls a baseband module through PoE cable and control FPGA through UART. SMA cables are used to connect the bridge boards with BPU. MCube provides large-scale phase arrays. It is equipped with a 2x4 array of 32 elements phase arrays. We will then give 3 demos showing the other capabilities. The first demo setup is to show the fast beam swapping and MIMO transmission capabilities. We used 2 MCube nodes, one as TX and one as RX. USRP N310 is adopted as BPU. The phase arrays are controlled by the same control FPGA. For fast beam swapping, we use the one TX and one RX phase array. The TX phase array is swapping 16 beams while the RX remains unchanged. The samples plot shows that each beam is occupying 11 microseconds, which can be shorter since the transition time of changing beam is negligible. The video shows that each transmission will start with the same beam index. This shows that the synchronization between the BPU and the control FPGA. Also, the swapping will be repeated if the sampling time is longer. Then, for the MIMO transmission, we use the two TX phase arrays and two RX phase arrays. The beam will be fixed, but the transmitting data from two TX phase arrays will be different to differentiate the channels. The received samples of two RX phase arrays are shown in the plot. This indicates that M-Cube can do the multi-chain communication. The second demo setup is to show the radar configuration. We use one TX bridgeboard and one RX bridgeboard on the same M-Cube node. The BPU is FMC DAC2, which supports 1 GHz bandwidth. This setup can act as a software-defined radar, where the FMCW waveform is generated and processed in digital domain. The radar function is software-defined, so the waveform can be designed flexibly. For example, it can also act as a UWB radar by sending UWB waveform. After processing, the platform can act as a distance detection radar. The peak here is corresponding to a person. As shown in the video, the peak moves along with the person. As a recap, M-Cube can reproduce the most unique aspects of millimeter wave radios in a programmable manner. It enables experimental research in millimeter wave communication and sensing with unprecedented flexibility. Compared with state-of-the-art millimeter wave platforms, M-Cube supports larger bandwidth, contains multiple phase arrays for MIMO, and a larger phase array. It can be connected with microwave SDRs and can do fast beam swapping. It also has many times lower cost. To summarize, M-Cube represents the first millimeter wave massive MIMO software radio. It has been open sourced and can be easily reproduced. We are also distributing M-Cube replicates to other research groups. Please refer to the project website for more information. Also, we have a paper and presentation in the main conference. Thanks for your attention.